Welcome to my channel Education Shop. In this video we will solve example 11.5 from the book Heat and Mass Transfer by A.Çengel, 6th edition. Here this statement is relevant about heating of glycerin in a multipass heat exchanger. Multipass heat exchanger means that the shell is 2, so that's why we call it 2 shell pass. In this heat exchanger, if you see that there is 2 shell, this is first shell, this is second shell. That's why we can say that 2 shell passes and the number of tube passes is 4. 1 2 3 4. That's why in combined we can say that 2 shell passes and 4 tube passes heat exchanger. Let's come toward the statement. At 2 shell passes and 4 tube passes heat exchanger, that is called multipass heat exchanger, is used to heat glycerin from 20 centigrade to 50 centigrade by hot water, which enters the thin walled 2 cm diameter tube at 80 centigrade and leaves at 40 centigrade. In this statement, the glycerin is considered as a cool fluid and the water is considered as a hot fluid. A convection heat transfer coefficient is 25 watt per meter square dot Kelvin on the glycerin's shell side and 160 watt per meter square dot Kelvin on the water tube side. The tube side convection heat transfer coefficient is 160 watt per meter square dot Kelvin, and on the shell side it is 25 watt per meter square dot Kelvin. Determine the rate of heat transfer in the heat exchanger. In the first case, before any fouling, and in the second case, after fouling, with fouling factors of 0.0006 meter square dot Kelvin per watt occurs on the outer surface of the tube. Let's make some assumptions. Whenever I write the small t, this is for the hot fluid. When I write the capital T, this is for the cool fluid. Now let's come toward the statement, what data it is provided in the statement, and also data is provided in this figure. We can also pick from this figure. You can also get the data from this figure. This is the cool temperature in. This is, let's say, T1, that is TC, cool fluid inlet temperature, that is 20 centigrade, and T2, this is cool fluid outlet temperature, that is 50 centigrade. Inside temperature of the hot fluid, temperature in of the hot fluid, that is 80 centigrade, and temperature out of the hot fluid, that is 40 centigrade. Diameter of the tube is 2 centimeter. 2 centimeter means 2 multiplied 10 to the power minus 2 meter. The length of the heat exchanger is 60 meter. Convection heat transfer coefficient inside the tube is Hi, that is 160 watt per meter square dot Kelvin, and outside of the tube is H0, and it is 25 watt per meter square dot Kelvin. But we need to calculate in the first case the rate of heat transfer in the multipass heat exchanger when no fouling is there. In the second case, the amount of heat transfer in this multipass heat exchanger when there is fouling factor, and its value is 0.0006 meter square dot Kelvin per watt. Now let's come toward its solution. The surface area of the tube is equal to pi dl. Pi value is constant. The value of d is 2 multiplied 10 to the power minus 2, and the length is 60. Just simply multiply and you will get the surface area of the tube, that is 3.77 meter square, and the rate of heat transfer is equal to overall heat transfer coefficient, surface area of the tube, correction factors, multiply log mean temperature difference. Surface area of the tube is calculated, log mean temperature we need to calculate, also we will find the correction and then overall heat transfer coefficient, and then we'll put the values in these equations, and just when we multiply with each other, you will get the heat transfer rate for the first case. We are solving now for the first case. Delta T1 is equal to, as you know, it is equal to temperatures of the hot fluid in minus temperature of the cool fluid out. That is, hot temperature in is 80 centigrade. This is 80 minus cool out is 50, and its value will give you 30 centigrade. Similarly, delta T2 is equal to temperature of the hot fluid out minus temperature of the cool fluid in. Hot out is 40 minus cooled in is 20. It will give you 20 centigrade. Now next we need to find is log mean temperature difference, delta T1 minus delta T2 divided by ln delta T1 divided by delta T2. Delta T1 is 40 minus 80. Delta T1 is 40. Delta T2 is 80 divided by ln 40 divided by 80. Solve in calculators and it will give you log mean temperature difference, and it is 24.7 centigrade. Next we will need to find the correction factors, that is called F. For that we will find the P and R, that is equal to T2 minus T1 divided by T1 minus small t2 minus T1 divided by T1 capital T1 minus T1. This is T2 is basically 40 minus 80 divided by T1 capital T1 is 20 minus 80. Solve this and it will give you the parameter P, that is 0.0 0.67. Next we will find the parameters R. With the help of this parameter P and R value, we'll find the value of F. You will see next how you will find. Parameter R is equal to capital T1 minus T2 divided by small letter T2 minus T1. The T1 value is 20 and T2 value is 50. Now the small letter T2 value is 40 and it's 80. Solve this on calculator and it will give you the parameter R, that is 0.75. With the help of the parameter PR and this graph, you'll find the value of the correction factor F. Here you can see on the y-axis you can see the correction factor value F, and on the x-axis you can see the values of the parameter P, and these curved line basically represent the values of the parameter R. Here you see the parameter P value is 0.67. It means that it lies over here. This is 0.6. This is almost 0.67 here. Now where the curve for the parameter R will lie when it is 0.75. If you see, this curve is for 0.8 and this curve is for 0.6, and our curve parameter R value is 0.75. So that's why I can say that 0 will lie between 0.8 and 0.6 curve, and this is, let's say, that line that represents the R value 0.75. Now I want to coincide this P value, that is 0.67 with the R value that is at this point. Here at this point, let's say at this point, if you move horizontally, you will touch the y-axis and you will find the value of the correction factor, that is almost 0.91. So that's why I can say that the correction factor value is 0.91. Next, to find the overall heat transfer coefficient, and there is no fouling factor, it is equal to 1 divided by 1 over Hi plus 1 divided by H naught. That is 1 divided by 1 over Hi is 160 and 1 over H naught is 25. Just simply solve this on calculator and it will give you the overall heat transfer coefficient, and it is 21.6 watt per meter square dot Kelvin. Now for the second case, amount of heat transfer without fouling factor is equal to overall heat transfer coefficient, surface area, correction factors, and log mean temperature difference. U value is 21.6, surface area is 3.77, and the correction factor is 0.91, and the log mean temperature difference is 24.7. Just solve on calculators and you will get the rate of heat transfer without fouling factor, that is 1830 watt. Next is to find the amount of heat transfer when there is fouling factor added. For case B, overall heat transfer coefficient will change only, that is equal to 1 divided by 1 over Hi plus 1 over H naught plus fouling factor, and just simply enter the value, that is 1 divided by 160 plus 1 divided by 25. Fouling factor is 0.0006. Just solve this on calculator and you will get the overall heat transfer coefficient, that is watt per meter square dot Kelvin. And the amount of heat transfer rate is equal to UA, surface area, correction factor, and log mean temperature difference. UA value is 21.3, surface area is 3.77, correction factor is same 0.91, log mean temperature difference is 24.7. Just solve on calculators and it will give you the amount of heat transfer with the addition of the fouling factor, that is 1805 watt. So in the first case, you see that the more heat transfer is observed, and the second case, less amount of heat transfer rate is observed. The reason is the addition of the fouling factor. Fouling factor is nothing, it is the debris, sediments either on the inside or outside of the tube. This explanation